did want to take a quick diversion here since we're going to be talking about pH and TA as we look at all of Corey's data. I wanted to take a quick diversion and kind of clarify those two things, particularly as they have to do with tartaric and malic acid. So when we look at kind of those organic acids that are found in grape juice, the two main players, of course, are tartaric acid and malic acid. There are other acids in there, but the things that are mostly driving the pH and TA are the tartaric and the malic. Once we get to the finished wine, if the wine has undergone malolactic fermentation, then of course lactic acid comes into play as well. When we think about kind of the acidity of these, we can think about that in terms of kind of what the definition of an acid even is. So by definition, an acid is a molecule that when you put it into a water-based solution, it's going to have some hydrogen ions that dissociate from that molecule. So when we look at tartaric acid and malic acid, you can see, well, there's lots of potential hydrogen atoms here that could dissociate, but not all of them do. It's only ones that are in a certain sort of conformation in the molecule. So if we look at tartaric acid, it's only the hydrogen ion that's affiliated with this sort of left-hand portion of the molecule, and then the one that sort of is associated with the right-hand portion of the molecule in a similar conformation. Both of those can dissociate at some point. So we would call tartaric acid a diprotic acid because it can give up two different protons along the way. I will say that they aren't given up at the same rate. So the first one is most likely to be given up. And then the second one, the conditions have to get more and more permissive in order for that second one to get given up. If you look at malic acid, you might say, well, malic acid looks a lot like tartaric acid. It's just missing that one little group on the second bump there. And so very, very quickly, you can predict that, malic acid also has essentially those same two hydrogen ions that it can give up into the solution. So malic acid is also a diprotic acid. When you look at lactic acid basically looks like the right-hand side of malic acid, whereas with that sort of left-hand side chopped off. So when we think about lactic acid only has one hydrogen ion per molecule that it can give off into the liquid to be acidic. So when we think about it from that point of view, which hydrogen ions are able to get given off and when they do, that actually helps us to understand both the pH and the TA of our juice and our wine. In order to kind of show that a little bit more clearly, I'm going to kind of turn this into a cartoon version. So if we think about that, if we look at our cartoon version here, all I've done is taken that sort of mother molecule of tartaric acid and just represented those two hydrogen ions that are dissociatable from that. Same thing for malic acid. It has those two dissociatable hydrogen ions. And then our lactic acid only has one each. Again, this would be sort of in that full acid form, but as soon as you put this into a water-based solution, as we said, some of those hydrogen ions are going to dissociate. So it might look more like this when you actually get it into the water-based solution. So, and you can see here is, again, you can see where if any given blue blob might have one hydrogen ion attached, two hydrogen ions attached, or no hydrogen ions attached. And again, the rate at which they give those up is slightly different between the different sort of base molecules. So if we kind of think about our acid dissociation in this sort of cartoon way, if we were to define what titratable acidity is, that basically represents the total number of hydrogen ions that could dissociate if all of the ones that are represented here did dissociate. So it means if we really force it so that the pH gets really high and it pulls all those hydrogen ions off, how many do we have? So in this case, the titratable acidity doesn't matter if it's currently bound to its parent molecule or not, just matters that it's in there. So if we, in our cartoon form here, I think we'd have 13 hydrogen ions that would contribute to the titratable acidity. The reason that the titratable acidity is associated with the sensory component of the wine is that essentially this is what's happening when the juice or the wine gets into your mouth. The saliva in your mouth is a neutral to basic buffered solution, and it pulls those hydrogen ions off of their parent molecule. So what you're actually perceiving is sort of the full amount of hydrogen ions that could dissociate in all of those acids. So that's why we measure the titratable. That's the relationship of titratable acidity to the sensory component of the wine. But of course, we also care about the pH of the wine. So if we think about what the pH is a measure of the total number of already dissociated hydrogen ions. So not all of the total ones that are in there, but the ones that are currently dissociated from the parent molecule. So in this case, I think I counted, we maybe have 7 hydrogen ions that would contribute to the pH of the solution. The pH is not just, it's not just grams per liter like we have for titratable acidity. Instead, this is in this kind of confusing metric of the negative log of the hydrogen ion concentration. So it is a measure of the concentration, but the fact that it's a log means that it's measured in increments of like 10 times as much. So a pH of 3 has 10 times as many hydrogen ions as a pH of 4, which means that there's a big difference between, say, even 0.1 shift in pH. That can actually be a big shift in the hydrogen ion concentration. The fact that it's negative is the reason why the pH, a lower pH, has more hydrogen ions, which is confusing, but we just have to live with that part. And it makes sense that the pH is the thing that sort of has the most to do with our microbial or our sort of microbial stability, because it's those free hydrogen ions in the solution that are floating around and interacting with the microbes in our solution. So it's really, I kind of think about it like those hydrogen ions are kind of attacking the cell membranes of those microbes and trying to destabilize the microbes. Well, if they're attached to their parent molecule, they're not really being active doing that. But if they're dissociated, they float around and they have that activity. So in this way, we can kind of, if we think about our pH and our TA that way, we can think, well, if we are comparing then our tartaric and our malic acids, malic acid and tartaric acid, again, are both diprotic acids. So they probably have a similar impact on the titratable acidity of the wine, because both of them have 2 hydrogen ions that could contribute if they were all stripped out. So they have a similar impact on titratable acidity, whereas like lactic acid, because we've chopped off that one side of it, lactic acid has less of an impact on the titratable acidity of the wine because it has fewer dissociatable hydrogen ions to participate. So when the wine goes through malolactic fermentation, we would hypothesize that the titratable acidity would go down because we're going from a diprotic to a monoprotic acid. But then we have to think about the impact of each one of these on pH. So as I said before, the amount of dissociation does depend a little bit on the structure of that parent molecule. And because of that structure, tartaric acid is a little bit more likely to give up its hydrogen ions to solution than the malic acid is. Malic acid is going to hold on to its hydrogen ions a little bit more. And lactic acid is going to hold on to its 1 hydrogen ion even more than that. So if we think about sort of molecule for molecule impact on pH, the tartaric acid is going to move the pH a little bit more because it's more likely to give up its hydrogen ion, and therefore it's more likely to increase that concentration of dissociated ions. Malic acid's kind of in the middle there. It's going to be it's going to push it less than tartaric, but more than lactic. And then lactic acid is going to give us less impact on pH. So again, the impact of malolactic fermentation, we would hypothesize that we would have a higher pH after malolactic because we have fewer hydrogen ions being given up to the solution.